Desmos. If you have a TI, you can actually input that information into your list 1 and list 2 in the TI. And if you go to the graph, I think you can press second stat plot, which one of the F keys it is, maybe the second, fourth one or something like that. And turn the stat plot on, and it will ask you which lists you're using. If you default to list 1 and list 2, then it will show you a scatter plot, and it will plot those points. In fact, it will give you the option of what the points themselves look like, whether they're an open dot, a plus sign, or something else, and that way if you have multiple things on the same screen, you can actually differentiate them. The other thing to be careful about is when you do that, if all of your points, so for instance, if I'm graphing this, x equals 5, y equals 15, x equals 7, y equals 22, the default viewing window to start is from -10 to 10 in both variables. I won't see any of these points, even if they're there, because I'm looking at a zoomed in part that does not include any of these points. If I zoom out, however, I'll be able to see these 6 points once they're in my lists. So just make sure to look for that. Make sure your viewing window includes the x coordinates and y coordinates of the points you're looking for, and then you should see them if they're in there correctly. Again, if you run into trouble with that, the book does have some information, but I'm familiar enough with it. You're welcome to email me or ask me in office hours. All right, so let's do this actually on Desmos and see how this plays out. So this particular question is about a basketball player named Amelia. She wants to improve in order to play at the college level. So she notices the number of points she scores in a game goes up based on the number of hours she practices her jump shot each week. Stands to reason that would work. And we have some data points with our input variable being the number of hours she practices the jump shot that week. That week, yes. And the output variable being the number of points she scored in a game. So again, when she practices her jump shot more, her points scored seem to go up. That's good. That's a good trend to see. We're going to construct a scatter plot and see if that scatter plot seems to give us the information that we're looking for. So let's see, 5, 7, 9, 10, 11, and 12. So when you go to Desmos, you go to the graphic calculator, the first thing you'll want to do, oops, that's not what I want to do, is click this plus sign and input a table. Okay, now for us, I'm inputting an x and a y into the table, so I'm going to leave it with these 2 variable names. But if you have something else you want to use, like if I wanted to use J for jump shot practice and P for points scored, I could do that. And it would then make it easier to interpret what my results look like. It will graph it just the same. Okay. Now let's see, what were my values here? 5, 7, 9, 10, 11, and 12. Here it is. So 5, if you press enter, it just allows you to input the next set of variables. And now let's see her points scored, 15, 22, 28. I think it was 31, 33, and 36, but yeah, that's right. All right. So those are my values. Excuse me. Now, I don't see anything, but it's the same issue I was talking about. All of these data points are up and to the right from my viewing window here. So in order to see those, I'm going to zoom out, and sure enough, there they are. Okay. And I also know in this particular situation, since we're talking about the number of hours she practiced, that has to be at least 0. And the number of points she scored, that also has to be at least 0. And so I really only have to look at the first quadrant for this graph. I can actually move it over here and get a lot more information. In fact, yeah, that's still a little too big. I'm going to change this, let's say 40. Oh, not my x values, I'm sorry. They can stop at 24, let's say. My y values, yeah, let's leave it at that. Okay, so the question is, she thinks that if she practices her jump shot more, her points scored will go up. Does this scatter plot give us enough information to say that seems likely to be true? Yeah, it's at least evidence in support of it, right? It's a small data set, right? Maybe something happened across those 6 weeks that somehow otherwise caused her to score more points. Maybe their leading scorer was slightly injured and was having trouble as the season progressed, producing as much as she had before that point. Who knows? But at least there seems to be some evidence that as she practiced more, her points scored went up. Okay. And as long as there's nothing else behind it to explain that, it seems like that might be a likely conclusion. So if we wanted to represent this as a linear model, how would we do that? Well, we want to find an equation y equals mx plus b for some slope m and some y-intercept b that might make that work. Now, I could just eyeball it and come up with an idea and get a basic feel for it. I'm actually going to do that here. And then we'll see how to produce the best fit line and see how that compares to the eyeball fit that we just came up with. So if I were to just extend this line here, I think my y-intercept is going to be about 4. And I have a point here that I'm going to say goes right through it. Let's see, that's 31 and 10. So using a point slope form, actually I'll just use slope intercept. My y-intercept is 4. And my slope is, as I go over 10, I go up about 31. So let's say 3.1. All right, so that's a little high. Maybe if I did 3.8, 3, 2. Okay, that's getting better. That looks a lot closer to me. So I think it's going to be something close to about 3.1x. Okay. I'll show you how to build the best fit line in just a moment. But before we do that, I want to talk about what we can do with these scatter plots, what we can do in terms of describing what we see there. If we want to use a scatter plot to draw a conclusion, we need to know what kinds of language we can use around them. And keep in mind, the correlation coefficient we're about to learn about is only going to tell us about linear relationships. Okay? There may be a clear relationship when we look at the scatter plot, but if that relationship is not linear, then the correlation coefficient will not reflect the relationship. So it's only going to test for a linear relationship. That's a key idea to keep in mind here. All right. So let's talk about scatter plots. What kinds of terminology can we use to describe those? And then we'll talk about, again, the difference between association versus correlation. Right? Just because two variables are associated doesn't mean that they are correlated in terms of a linear correlation. And of course, that's entirely separate from causation, which is a difficult thing to prove statistically. Okay? It takes a lot more robust information. We will then turn our attention to building the line of best fit. We'll describe exactly what that process looks like. It turns out it's not hard once you know the correlation coefficient to build it from there. But computing that is a bit tedious, and so as I've encouraged you for most of this term, use a calculator. It will do all the hard work for you. All right? I often like to have students do this by hand one time just to see it, but it amounts to a calculation very similar to the variance calculation that we did early on in the course. You can compute those things by hand, and you can compute the best fit line that way. But it's probably easiest at this point to go ahead and just use the calculator. Now, excuse me, I will introduce a new calculator that we will unfortunately have to use for this module at least. It does allow you to do some other calculations for the other modules, but the number of decimal places it gives you, unfortunately, is not enough. So we can't quite use it for instance, the hypothesis testing we were practicing this morning. This other calculator is called Vassar Stats. It's from, I forget the individual's name at Vassar College. And the thing it does that Bogdanar's calculators and the Desmos will not do is it will actually run a hypothesis test for our correlation coefficient. And so that's a separate type of hypothesis test. We're basically testing whether it's different from 0. But it has to be run under different conditions, and our regular calculators don't have that option. So we'll have to use this one. All right. So let's jump straight into the scatterplots, okay? Now I'm completely separating these scatterplots from any set of axes. I don't necessarily need you to think about a particular scale or anything like that. It's more about just thinking about what kinds of trends you might see here. So if we look at this particular one, it does seem like my horizontal direction and my vertical direction are somewhat correlated, right? If I were to try to describe that with a single line or curve, this one I would call a curved relationship. And this one I would say is far less curved. This is much more straight. Okay? And so that's one thing I can describe. I can also talk about what happens as I move forward. Does it go up or does it go down? Okay? And so the first thing that I'm going to describe here, this is a positive trend. As I move to the right, my y values, my vertical values, go up. So that's positive. You think of it in terms of the slope, it's positively sloped. And this is a negative correlation, a negative relationship. So these are moving down as I move to the right. Okay? So if I talk about the form of the shape, this first one is slightly curved, because again it has just this gentle upward curve. And this is sharply curved because if I were to draw this, it looks almost like a sine wave. It's a very sharp, complete turn. Okay, so that's sharply curved versus slightly curved. And what about these? Well, this is a strong correlation because I can see very clearly as I move from left to right, there's a very strong relationship between what's happening to the y values. This seems like I just took a handful of dots and threw them at the wall. Right? They just landed wherever they landed, and there was no necessary relationship as I moved left to right. And so this is about the strength of the correlation, or the strength of the association between these inputs and outputs. This is a strong association. I can see a clear trend as I move from left to right. And this is a weak association. It's very hard for me to know from my left and right movement what's happening vertically. All right. So when you're talking about scatterplots and you're trying to decide whether you can use a linear model, you should decide which variable you want to be your response variable. That's the variable you want to study. Which variable you're going to use to predict that variable or to explain it. And that will be your input variable. And so your input variable will be on the x-axis, your output variable or response variable will be on the y-axis. And from the scatterplot, you should try to assess what directionality do I see. Is there a positive trend? Is there a negative trend? Is it really hard to determine? What form do I see? Is it curved? Is it straight? Is it slightly curved? Sharply curved? Is there a curved type that it seems to follow? Look at the strength. That is, when I'm looking for an association moving left to right here, do I see a strong relationship or do I see a weak relationship? Does it look like it's just a lot of noise? Or does it seem like there's a clear trend as I move from left to right that I can understand? And then ask yourself from that, is that trend linear or not? And of course, look for unusual features. One of the things you might look for there are values that are way away from the rest of the group. For instance, if I go back, if I had this scatter plot, but there was one extra point that was, say, over here, that would be a pretty unusual feature to notice, and I would ask a lot of questions about that point. It doesn't mean that that point is nonsense and shouldn't be included. It just means that there's clearly something interesting happening there, and it's worth exploring where that came from and what effect that might have on the legitimacy of my model. So, if I look at a scatter plot and I think that there is a relationship, how can I decide how strong that relationship is? Clearly I can tell the difference between things like this relationship and this one. This is a very strong relationship and this is a very weak relationship, and that's pretty obvious just visually. But if I were to move one of these points, say from here to here, the relationship clearly becomes weaker, but how much weaker, right? Can I really find a way to compare those? And if I had another one that looked somewhat similar to this, but had maybe a couple points out of place, how would I be able to quantify how much stronger one relationship is versus the other. And that's where our correlation coefficient will come in. So how do we do that? Excuse me. Well, this is where the notion of standardization actually comes in. So when we talked about the normal distribution, one of the nice things I said about that is it allows us to compare variables that aren't on the same scale and decide how unusual one value is compared to another. So the examples I gave were things like a perfect score in the SAT and a 4-minute mile. Those are both unusual and great accomplishments. Which one's more impressive? If you're a sports fan, you can talk about, I think it was the Seattle Mariners who had, I forget how many wins they had, but it was the most at that time in a 162-game season, versus the Golden State Warriors had 73 wins in an 82-game season in the NBA. And the question is, which one of those things is more impressive? And extreme win percentages are a little bit more common in the NBA than they are in the MLB. Things tend to be much closer to a 50% win percentage in MLB just because scoring is low. A lot is dependent upon the pitcher in a given day, and there's a lot of, I guess you'd say, randomness that takes the likelihood of the better team always winning being a little smaller. Long story short, when we standardize, we compute a z-score for each of those things. It gives us a common scale to compare them on, which is essentially how many standard deviations away from what is normal for that group was this particular individual. If they were more standard deviations away, they were a more unusual event. Right? 3 standard deviations away is more unusual than 2 standard deviations away, even if you're looking on different scales for what standard deviations happen to be. So that gives us a way then to compare those different things. Well, in the case of correlation coefficients, we can actually use those standardization values both for our explanatory variable x and our response variable y. And when we do that in this way, which I'll describe in just a moment, we can compute a value r, little r, which is called the correlation coefficient. Okay? And if you've seen this before, it's called a Pearson correlation coefficient for the person who first described it in this way. But the correlation coefficient is computed as the sum of the products of the standardization of the x value and the y value for each point. So remember, each of these points has an x and a y pair. This point, for instance, is paired here and here, so at about 1.2 and 5. And so this point was 1.2 standard deviations above the average for the x value, and it was 5 standard deviations above the average for the y value. And the question is, what does that do? Well, in practice, I'll be taking the number of standard deviations x that I have here and the number of standard deviations y I have here. If both of those are positive, then that point will contribute towards a positive relationship, a positive trend. And it kind of makes sense because points in this direction are moving to the right for the x's and moving up for the y's, and that's the trend that a positive trend should represent. The same thing is true for points in this region. Right? I have negative values for my x standardized form and negative values for my y standardized form, and when I multiply two negative signs, I get a positive number. So these will also contribute to a positive trend, a positive value for r. On the other hand, points in this region and points in this region will result in a product that is negative, and so they will point towards a negative trend line, a negative correlation. In practice, these r values are always between -1 and 1, excuse me, and the closer they are to the extremes, the more linear that relationship is. In fact, if I get +1 as my correlation coefficient, I have a perfect fit for the line. That means every point is on the line, and it has a positive slope. Similarly, if I have a -1 as my correlation coefficient, I again have a perfect fit for my line, meaning every point in this scatter plot is on the same line, and the slope is negative. So the sign of R tells me generally the slope that I would see, whether it's positive or negative. And if it's one of these extreme values, then it's a perfect fit. Every point is actually on that particular line. The smaller my R value is, or the closer it is to 0, the less linear the relationship that I see happens to be. Okay, so if I were to go back a couple slides, this will have an R value pretty high, probably about 0.9-ish, right? It'll be a positive R value because the trend here is clearly positive, and it's a very strong relationship, so it'll be close to 1. I'm going to guess about 0.9, maybe even 0.96 or something like that, a pretty high R value. That tells me that there's a strong linear relationship. Okay. This one, on the other hand, is going to have a much weaker relationship. If I were to look at it, it does seem like there's still a slightly positive trend here. So I expect the R value will be positive, but it's going to be small, close to 0, probably about 0.2-ish, something like that. So that will tell me that there is somewhat of a relationship, but it's not a very strong one. At least it's not a very strong linear relationship. And I will warn you, just because the R value is close to 0 does not mean there is no relationship. It just means that there's not a linear relationship, at least not evident from that data. Okay. All right, so when we compute those products, add them all up, if we divide by n minus 1, where n is the number of ordered pairs we've considered, that gives us the correlation coefficient. And of course, you can compute this by hand, but I do not recommend it. Your calculator will do this for you, and this would be a lot of calculations to do here, because first of all, you have to compute the z-scores for every one of those, which requires you to know the mean and the standard deviation for x, and the mean and the standard deviation for y, and then to standardize each of the x's and y's that you see in the entire set. Calculators can do this very quickly and very efficiently and very accurately, all at once. Okay. Now, if I want to use, if I want to use this correlation coefficient to decide whether I have a linear relationship or not, and then to perhaps produce a linear model that I plan to use, I do want to check these 3 conditions before that correlation can really be used. First, the 2 variables that I'm looking at have to both be quantitative, right? If I have an association between a categorical variable and another categorical variable, or a categorical variable and a quantitative variable, that association is not valid for correlation coefficients. I cannot use a correlation coefficient if either of the variables involved is categorical. I also want to visually inspect to see, does it seem like I have a roughly linear relationship? I call this a straight enough condition. Essentially, do I see what looks like a linear relationship here? If I were to go back to this one, this pretty clearly tells me that I do want to use a correlation coefficient. I see a pretty strong linear relationship, and so it's worth my time to try to build that best fit model and see what that tells me. This one, on the other hand, maybe I'll get some information here, but it doesn't seem like it'd be very, very reliable. This relationship doesn't really seem to be linear, if there's a relationship really at all. I see a lot of noise here that it's hard to decide if there's a relationship that's present. All right. And then the last condition to check, look, hopefully you're in a situation where there's no outliers. You should always check for those to see, because they can, of course, distort the strength of the association. If there are outliers, it's not necessarily that you should throw those out. In fact, I strongly discourage you from doing that. But it's more about understanding where those outliers came from. Is there a reason why you see that unusual behavior for that one point? Or is it just that there's some variation there that happens to produce those kinds of things by random luck, by unfortunate luck? Okay, so again, you've heard this plenty of times before, but just because I see a strong correlation does not mean that my explanatory variable causes my response variable. When I see a connection between those things, there are lots of ways that that connection could come about. It could be that there's something they have in common that causes them to both occur at the same time. It could be a common cause in that situation. Or there could be other ways that they are both connected to some other variable that then leads to that connection. It does not necessarily imply that one causes the other. Okay? Plenty of examples out there. I'm not going to go into those today. When we have multiple different variables that we are considering connections between, we can often try to look at the correlation between any two pairs of those variables. And when that happens, what we'll do is we'll produce a correlation table. And so you can read a correlation table by looking at how, for instance, in this case, assets are corresponding with assets. Well, if I plot X and itself in the XY pair, that's complete correlation, right? If I know X, I immediately know the Y. So that's why I get an R value of 1 here. And the same thing is true when I compare sales with sales, market value with market value, and so on. Okay. But when I try to compare sales with assets, okay, sales is my input, assets is my output, I get a correlation coefficient of 0.746. So that's a relatively strong relationship. It's not stellar, but it's present. Okay? And you can see that these relationships seem to be getting weaker in this particular case. Our market value and sales correlated. The correlation coefficient there was 0.879. And again, you can read the tables just like that. You'll notice in this particular example, the upper half of this table is empty, and that's because if sales and assets have a correlation coefficient of 0.746, then assets and sales will have exactly the same correlation coefficient, 0.746. So there's no point in showing it in both directions. It's going to be perfectly symmetric, so we really only need to fill in one side. In this case, we chose the lower triangular portion. Those of you who work with matrices, this is a lower triangular matrix, and you can think of the uppers as irrelevant here. They're the mirror image of this. All right. So that's what correlation is. Now, it can be calculated by hand, like I said, using this formula, but it's a lot easier to let your calculator do that for you. And given the time that we have here, I'm going to talk about a linear model and then show you how to build it. Build the first linear model we'll do in Desmos before we take our next break. So the type of linear model we're going to use is what's called least squares regression. And essentially what it does is it takes a y equals mx plus b form and compares the predicted value of y with the actual observed value of y. And what we do there is we subtract those two things. That gives us something called the residual. And then we add up the squares of those. So similar to how we calculated variance before. If you add up the squares of those, and you look at what that does as you change the slope and the y-intercept of the line you're using, you will find that there's a quadratic function that you can minimize. And if you can find a way to minimize that function, find out where the minimum happens to be, those of you who've taken algebra, you may recall the minimum of a quadratic happens at the vertex. It's not hard to find that in many cases. That allows us then to find the best fit, the best slope, and the best y-intercept that will happen to work. The result as a line is a model for our xy pairs in the scatter plot, and that is what is called the least squares regression line. Okay, it is the best fit that minimizes the sum of the squares of the residuals. Okay. So just to emphasize that, if this is the situation I'm trying to model, maybe I'm looking at protein content and fat content, and obviously I might expect that if there's more protein, there might be more fat, because if nothing else, there's probably more actual food involved here. So I expect there might be a linear relationship. If I were to run that entire least squares regression process, maybe this is my best fit line. Well, at this particular location, this point had an x value of about, looks like 37-ish, and a y value of about 18. But my model, this red line, predicted a y value of about 42. So we'll use this notation y hat as my predicted value, and I'll use y as my observed value. And the difference between those two things, this gap right here, is what's called the residual. And when we're looking at this sum of the squares of the residuals, we're actually computing the residual for every single point here. We're comparing this point to the line. How far above it did it fall? How far above here? How far below here? How far below here? And we take each of those differences, square them, and add them up. The best fit line is the one that produces the minimum in that total sum of squares. Okay. And once we've done it, we'll write that formula as essentially y equals mx plus b. The notation that we typically use in a statistics setting is y hat equals b naught plus b1x. Okay, I'm just going to use those particular coefficient names. B naught here is my y-intercept from the model, and B1 is my slope from the model. Okay. Now, I think in the TIs they may use A plus BX, or they may use AX plus B. You can actually write it in either form. Just remember which one is the slope and which one is the y-intercept. As a recap, the slope is always the coefficient of x, so it's the thing in front of the x. Now, when you think about how you can interpret the meaning of those things, this is one of the nice properties of linear regression. We know what the slope and the y-intercept are supposed to tell us about a line, and so if we're modeling a real-world situation with this line, we can interpret what the slope and the y-intercept mean in the same way. So let's start with the y-intercept. Where do you find the y-intercept for a line? Where would it actually be? For instance, if I was looking at this line.
On the y-axis?
Right. It's on the y-axis, which is specifically where x equals 0. Right? Remember, you can always find the y-intercept for any function by plugging in 0 for x and seeing what comes out. Well, in this case, if I plug in 0 for x, that will tell me what that y-intercept means. It is my predicted value when x equals 0. So you can think of it as the predicted y value when x equals 0. In different situations, that will have a different meaning. And in some situations, that will have a nonsensical meaning. There will be nothing that can possibly tell us of value. But in many cases, it will tell us something of value, and if it does, that's how we know what it means. Ask yourself, what did it mean for x to be 0? This is the prediction for y in that situation. All right. What about the slope? How do we interpret it? This is a little harder.
I just remember rise over run. So.
Okay. So the rise is the change in the y values, and the run is the change in the x values, right? So you can think of it as the change in y per the change in x. And in fact, in most situations, if you have units for your y's and units for your x's, those units will actually tell you what the slope is doing. It's computing an average rate of change. As your x values go up by 1, what happens to your y values on average? Okay. And so as long as you can state it in terms of units of y per units of x, that almost always makes clear what that average represents. If I'm looking at distance traveled over time, then my y units would be the distance traveled, maybe it's miles, and my x units would be the amount of time, maybe it's hours. And so if I compute a slope there, the units would be units of y per units of x, which would be miles per hour. It should be pretty clear that that's an average speed. And if nothing else, I know that because that's what miles per hour are used for. Okay? So if you do the same kind of thing, you think about your units of your y variable and your units of your x variable, and you say units of y per units of x with the correct number for the slope, you'll usually be able to interpret what that means correctly. It tells you an average. How does the y value change as x goes up by 1 on average? All right. So, if we want to find the least squares line, what do we need? We need a correlation coefficient. In fact, you can build the slope from that. I'll show you that formula here in just a moment. We need the standard deviations for each one so we can find the scaling factor and also for those units. And then we also need the means for the inputs and the outputs, so we know where the line itself is going to fall. Okay, so if you're building this by point slope form, what you'll do is you'll compute the slope that you need, and then you'll take the average x and the average y as a point on your best fit line. It's kind of an interesting feature that when you build the best fit line, your average x value and your average y value as a point, it may not be in your set, but it will be on the best fit line. It's guaranteed to always be there. So that's a point you know will be there. And the slope can actually be determined from both the standard deviations and the correlation coefficient. I'm giving you this formula. I don't necessarily expect you to use it. I don't believe that it comes up on the homework, but don't quote me on that. It's been a while since I looked at this particular homework. The slope is given by the correlation coefficient times the ratio of the standard deviations, where the standard deviation of y is divided by the standard deviation of x. Okay. And notice that the units for this slope will be units of y per unit of x. This is unitless. This has units of y because it's standard deviation of y, and this has units of x because it's standard deviation of x. So that will give me the correct units, and it will actually give me the correct slope for the best fit line as well. And as you might expect, if I have a higher value of r or a lower value of r, I'll get a higher slope or a lower slope here, respectively. All right. So the key idea I've tried to mention here is if you are doing this by hand, this gives you a way to do it. You can build the best fit line by computing the slope this way, and then using this average point. It's like a midpoint, but it's like the midpoint across all data points you have. And that's an average point. That point will be on your best fit line. And then from there, I have the slope, I have a point, I can build the point slope form of the line. Okay. We're going to do this example in just a minute, but first I want to show you how to use Desmos to compute the best fit line for this example. All right, remember this was my prediction based on what I saw. I can actually see that that's not going to be quite the best fit line because it does go between most of the points, but it seems like here it's falling a little bit below. Okay, so I want to avoid the situation where as time goes on, my line fits less and less. That's generally a bad situation. That tells me that I may want to look at a nonlinear relationship or a different line, one of the two. Now let's see how can I compute this. Well, if I want my best fit line, it's going to look something like y equals mx plus b. And I want to predict it in terms of this y and this x. Now I call them y1 and x1. So when I'm building a best fit line, I'm going to use, instead of y1 equals mx plus b, I'm going to use a tilde. And what that does is it tells Desmos I want to build the best fit of the type I'm about to show you. Okay. Now if I tell it mx1 plus b, now it's going to build the best fit line. And it gives me my correlation coefficient. It's pretty darn high, 99.76%. That's pretty high. And my slope, my guess here was 3.1. My slope is actually 2.97. And the y-intercept is about 0.76. Okay. Now let's think about what these two things mean in terms of the linear model here. Oh, I forgot I could plot the residuals here as well. If you click that button, what it does is it computes the residual. The residual is the difference between the actual y value and what this model predicts. So this point was a little bit below the predicted value, and you can see that here. This point was a little bit above. There it is. This point was a little bit above, below, and below. And that's what's showing up here. It also plots those residuals in this case. And again, this line is the one that minimizes the sum of the squares of these numbers. That's why it's called the least squares regression line. All right, so that's all we need to build that best fit line. Now we can also interpret it if we think about what these units are telling us. So what are my x values here for this example? Do you remember what these were?
Hours of practice?
Right, hours of practice with her jump shot. Right, this is Amelia practicing her jump shot each week. And the number of hours she practiced her jump shot that week was the X value. What was the Y value?
Score.
The points that she scored in the game that week. So if I were to try to interpret what this slope says here, the slope here is 2.97. If I were to interpret that slope, what I can do is I can say the number, 2.97, and then units of y per units of x. So here that would be 2.97 points scored in the game per hour practicing her jump shot. So for every hour she practices her jump shot, on average, she scores 2.97 extra points. That's what this slope is telling us. If she wants to score 9 more points than she scored this week, then to average that, she would need to practice another 3 hours. 3 times 2.97 is about 9. Okay. That's what this model is telling us. Now what about the y-intercept? The y-intercept tells us the predicted value of y when x is 0. So let's think about that in reverse. X is 0 when she practices 0 hours. So if she doesn't practice her jump shot at all, the y-intercept tells us the predicted points she will score. Right? And we can see from this that she's predicted not to score very much at all. Basically 1 point. We think she'll hit a single free throw, and that'll be it, on average. In fact, a little bit less than that on average. If she does not practice her jump shot at all this week, then on average she will score about 0.765 points. That's what that y-intercept tells us. Now there's some questions to ask yourself when you try to use that for interpretation. First of all, does it make sense? And sure, it does. I'm not predicting a negative number of points, so that's not so outlandish as to be completely false. But I also need to look at the data I have. The data I have here, she practiced at least 5 hours, and at most 12 hours. So if I try to use this model to talk about what happens at 0, that's kind of far away from my first actual data point. It's hard to know if this model that seems pretty accurate in this region is still accurate over here. And here's another question. If the slope here is 3, roughly, then if she practiced a lot 1 week, maybe she practiced 33 hours, well, if you multiply this by 33, you basically get 99. And this is basically 1. It's going to be a little bit less than that, but ballparking it, this model predicts that if she practices 33 hours, she'll score 100 points in the game that week. Does that seem likely to be true? Obviously not. And the reason that we should be dubious of that is not just that that's a huge number of points, but also that's very far away from the points that we have here. Our maximum x value in our data set is 12. And so if we try to draw a conclusion about what happens at 33, that's pretty far away from that. We should be a little bit careful about what conclusions we can actually draw that far away from the actual data we have. Okay. The thing about best fit lines is they can be great for interpolation. That's making a prediction within the range of the data that you have, so somewhere in this region. If I wanted to predict what would happen if she practiced exactly 8 hours, I don't have data for that, but I can use this model to predict. If she practices 8 hours, she'll score about 24.5 points on average. Seems like a reasonable prediction. I can even use it for extrapolation, predicting outside the range of the data. Like here, if she practices 13 hours, and I think she'll score 39 points. That's not unreasonable given the trends that I'm seeing here. And it's relatively close, so I find it believable. So, we will build a linear model for this example in just a few minutes. This is one of my favorite examples. Those of you who have been in my algebra class before, you may have seen this model. I really like to use this one because it's real-world data, and it actually gives you some information that you might not know up front, but that is an interesting question to ask. And so I'll talk about this When we return, I think this is a great time to take our second break, and then we'll talk about how to calculate the best fit line in this situation, how to make predictions using it, and how to interpret what we get from that information. So let's take a 5-minute break. On my clock, it is 10:49. So let's return at 10:54.